Hello. Today we're going to show that if I have a function f from x to y, x and y are sets, and g, a function from y to z, where y and z are sets, that if f and g are onto or surjective functions, then the composition of g and f is onto, or again, surjective, depending on the text you use. Surjective and onto are the exact same thing. I'll try to write both. So the situation we have is, let's say we have a function f, and these are sets x and y. F takes an element here, and this is the set z. Now I'm doing capital X, Y, Z's to differentiate. And G will take an element from here to here. So we're saying that F and G are both onto. So what we want to show is that the composition G of F is also onto or surjective. So what do we want to show then? Well, let's write this a little more mathy. So we want to show that for all z in the set z, there exists an x in x such that g of f of x is equal to z. Z, the element, not the set. It's hard to differentiate when you write. So fancy z, or the big Z is the set. Okay, so another way to write this, if you like, this notation that for all z in fancy z, they'll exist an x in x such that, I'm going to do wrong composition, g of f of x equals z. So this is what we want to show. If we can show this, then we have proven that the composition is onto or surjective. So here's the proof. It's not very long. We're going to do it directly. So first thing we say is let z be an element in z. Don't like that. And let's say this is arbitrary, meaning it's not a particular z, it's just some z in that set. And we know these sets aren't empty. We're going to assume that there's elements in these sets. So the first thing we're going to notice is that since we assumed that G is onto, again, surjective, depending upon your book, text, professor, both mean the same. There exists a y in y such that, st, I put such that, g of y is equal to z. This is the definition of surjection, right? It's every element in the codomain there's an element in the domain such that the function maps to every element in that codomain. Let's maybe write that. Let's say that we have a set A to B. And so onto, by definition, will mean that for all, and we'll say that the function h goes from A to B. That means for all A in A, there exists a B in B such that h of B is equal to A. So this is a definition of onto. Now that was clear, hopefully, in the we want to show, where we essentially just wrote down the definition of what it would mean for the composition to be onto. But just so we're clear, that's what onto surjection means. All right, so we assume G is surjective, so there exists a Y in the set Y such that G of Y equals Z. Now we also assumed that F is onto. So this means there exists a X in the set X such that f of X is equal to Y. Again, this is a definition of onto. So F is onto G of onto. So now let's look at what F and G, or G composed of F, is. Notationally, this is the same as saying that G is of F of X, meaning that if I have a function G, I input X, F of X, into G. And we set up here, because F of X, or F is onto, F of X equals Y, so this is equal to G of Y, because we're replacing F of X with Y. And above, since G was onto, we know that this is equal to Z. So that means that G of F is equal, or G of F of X is equal to Z. And since Z in big set Z was arbitrary, we can conclude that for all Z in Z, there exists an X in X such that G of F of X is equal to Z. This is the definition of onto surjection. Therefore, G of F is surjective. And we are done. So we just use the fact that F and G are both onto, both surjective. We wrote down what that means for them to both be surjective. And then we looked at what the composition was for some element X. And that's it. So we've proven that G of F is surjective when F and G are. That's it. Thanks for watching. Like and subscribe, and we'll see you in the next one.